Okay, we have here to another integral. We've got the integral of 1 over 1 plus cosine 2x dx. Okay, I recently did the same problem on my other channel and it went really quick. We did it with the straightforward method, just using some trig identities, and it was a really easy integral. And now in this video, what I'm going to do is use an alternative method. We're going to use the complex definition for cosine. So this is not going to be the fastest way, not even close. So if you want the faster way, I'll provide a link to that other video. Okay, now to get started with this, let's just look at the complex definition for cosine that's derived from Euler's formula. We've got, for cosine x, we can write this as e to the ix plus e to the minus ix all over 2. So using this, we'll just rewrite the integral. We'll have our dx, and this is going to be 1 plus cosine 2x. So all I need to do is we'll just input 2x into this in our exponent here. So this is going to become ei 2x plus e minus I 2x all over 2. But now I want to get some simplification. I want to get this 2 out of the denominator here. So what I'm going to do is I'm going to multiply in by 1. I'll multiply by 2e I 2x, and we'll do the same thing here in the numerator. So when I do this, our numerator is going to become 2e I 2x dx. Now multiplying this to the first term, we're going to have 2e I 2x here. Now for this part, the 2's are going to cancel, so we'll just multiply ei 2x times ei 2x. This is going to give me ei 4x. And then when we multiply it on the last term, the 2's are going to cancel, but then we're going to end up with e to the 0. So this is going to just be 1. And now what I'm trying to do is set up a u substitution, but I need to do a little factoring first. We can actually factor, just notice if you think of this term, if we just call that t, for example, well then this is t squared. So what I can do is factor this like ei 2x plus 1 all squared. Because notice when we square this term, we get ei 4x. The middle terms, we get ei 2x times 2, and the last term is just 1. And then we'll just copy over this numerator. But now I have this set up for a u substitution where I'm just going to make this here my u. So we'll come over here, we'll say u is going to be ei 2x plus 1. I'll take a derivative, so du, derivative of 1, 0, derivative of this is going to be ei 2x. But with the chain rule, I need to bring a 2i in front, and we'll have a dx. So then you'll notice that this here is really similar to our numerator, but not quite. We're missing that I right there. So what I can do is, let's just create that so we can set up this substitution. So I'll just multiply in an I here, but I don't want to change it, so we'll multiply by 1 over I in front. And now I'll just go ahead with this. We're going to have our 1 over I in front. Again, the whole numerator just became du, and this is just going to be u squared. But now the integral of du over u squared, this is just going to give me minus 1 over u. And then we'll have this 1 over I in front. I'm just going to leave it like that for now. And we'll go ahead, we can back substitute with our u values. This is going to become, let's just write it like, we'll have our minus 1 on the numerator. We'll have this I here. And then this is all going to become ei 2x plus 1. But now at this point, I don't really like it in this form, because what I want to do is I want to get it back to where we can use cosine, sine, tangent. And so notice our form here, we have our form for cosine, we have eix plus e minus ix. So what I can do to try to clean this up is we'll just multiply by 1, multiplying by e minus ix. But then having this in the denominator, that's going to help me clean up this piece. So then we'll multiply this stuff all together. We're going to have minus e minus ix here. Then the denominator, this is going to have, we'll still have our I. This is going to become e ix plus e minus ix. And that's starting to look more the way we want it. But now at this point, I was a little bit stuck, because again, I want to get this to look like sine, cosine, tangent. And this doesn't really work what we have here in the numerator. Now I know it's not going to look like cosine or sine, but let's look at the complex definition for tangent. So with our complex definition of tangent over here to the right, you'll notice our denominator is all set, right? We've got the exact right denominator here. But we also have in the numerator all this stuff over here on the right. We already have that here in our numerator. We're just missing this piece right here. So then my dilemma is, how do I add that back in, but without changing the value of our answer? Well, the nice thing is, of course, this is an integral, and so really we have a plus c right here. And we are free to kind of mess with this plus c a little bit. I can kind of break it up. You know, I can write this as like c1, c2. And so I'll leave this one alone, but I'm free to mess with this constant as much as I want, right? As long as it's a constant, I can do what I need to. So what I'll do here is, for this c1, let's call it 1 over I for now. And 1 over I itself isn't going to help me here, but if I get a common denominator, now I can add this constant into whatever we have here. So let's see how this is going to work. If I have, to get the common denominator, I just need to multiply here by EIX plus E minus IX. And we'll do the same thing in the numerator. And then I just need to bring down all this stuff right here. So we have, and then again, everything we've done here, even though there's an X in it, this whole thing is just 1. And 1 over I is a constant. So this piece here is still a constant. We didn't do anything to change anything. But the tricky part now is if I just add these together with the common denominator, notice that this term and this term is just going to cancel. We're left with this when we have the same problem we had before. Well, what I can do to fix that is I can just multiply in by 1/2 here, so that way we'll preserve both terms. And again, half's just a constant, so this is still just my C1 value. So let's add this whole mess up together, and we're going to keep our denominator with just as it is and just rewrite it. So this is going to be the same thing here. First, we're going to have this term right here, so we'll have 1/2 EIX. And then here, distributing in the 1/2, we're going to have 1/2 E minus IX minus 1 E minus IX. This is going to give me minus half E minus IX. But then I can just rewrite it. We've got half in common here, so I can bring 1/2 in front of the whole expression and rewrite it as just EIX minus E minus IX over the same denominator we have originally. And now our C1's gone, so I don't even care about calling this C2. I'm just going to call this plus C. But then notice the way we have it right here. This is actually our definition for tangent that we have right there. And so with this being tangent, I can just write down my final solution, 1/2 tan x plus C, and that's it. Okay, so there you have it, making an easy integral much more complicated. Thanks everyone for watching. Have a good day.